Okay, this will be the examples video for lesson 8, which covers the discrete probability models, the binomial model, the geometric model, and the Poisson model, and also expected value, mean, and standard deviation for those discrete probability distributions. These videos would be more practical in classes like honors, finite math, brief calculus, and AP statistics. Okay. So first problem here says a fair coin is tossed 6 times. Find the probability that exactly 4 tails appears. Find the probability that no tails appear. Find the probability that up to 3 tails appear. Find the probability that at least 2 tails appear. So pause the video and give these a try. Remember, you can use binomial, geometric, one of those kind of models to solve this problem most efficiently. Okay, so the first thing we should ask is if we have something where we're doing a trial, the same thing over and over and over again, could it qualify for one of our standard models, right? And do we have a yes or no condition? Yes, in this case, the yes is that we have tails, right? We're talking about getting tails. So yes on one trial would be getting a tail, so that criteria is met. We also have to have the probability is constant, right, and independent. Those are really two separate things. But in this case, a coin doesn't have any memory, so that means the probability of getting a tail is the same for each trial, so that would be met as well. And then specifically, do we have a fixed number of trials? If we have a fixed number of trials, then that would make this a binomial. In this case here, we have specifically 6 times, and we're talking about a number out of that 6 being tails. And so that also is true. And so that means we're going to proceed with using the standardized binomial geometric model. Okay, so that'll be our con model for that. So you should always check that first, because if you can use those things, it makes it much easier than trying to solve with the foundational probability and OR rules and all trees and all that kind of stuff. Okay, so as soon as I detect that, then I'm going to create a random variable. In this case, it's going to represent the number of tails in 6 tosses, right? And then I'll list out the possible values, right? I could have no tails at all, or 1, or 2, or 3, or 4, or 5, or all 6 of them can be there. And then I can figure out the probability associated with each of these things using one of the binomial calculator functions. So for part A, we're talking specifically about the probability of having exactly 4 tails, right? So exact cases, like exactly one of these cases only, we use the binomial PDF, the particular specific solution, right? Binomial PDF, right? Binomial PDF, and then you have to say, okay, it's out of 6 total trials. Now, we'll have to figure out what the probability of success is. So the probability of success would be the probability of getting a tail. And so since there are 2 sides to the coin and it's fair 1/2 of the time, we should get tails, or 0.5. So I'm going to put 0.5 in there. And we want the probability of having exactly 4. So this would be a job for the calculator then. So if we pull up a calculator, we can go, let's see, under second and the distributions menu, second bars, scroll down to the binomial PDF version. You want to make sure you get the PDF. C is for cumulative total of multiple cases. So out of 6 trials with a 50% chance of success, having exactly 4 be tails, that would be 0.2344. So the answer to that is 0.2344. Okay, so for that one, we're talking about an exact case. We use binomial PDF, and we use binomial because we're finding a number out of a fixed number of trials. Okay, for part B, we're finding the probability that no tails appear at all, right? So that's another exactly equal case. It's just the case of having exactly 0 tails. So we're finding the probability of exactly 0 tails. So we'll use the same as above. We'll just change the 4 to a 0, right? Out of 6 trials, 50% chance of getting tails. The probability of getting 0 tails would be 0. And if you do the same calculator sequence there, you get 0.0156. Okay, so for part C, it says, what's the probability that up to 3 tails appears? So up to 3 tails appears. Okay, so that means we could have 0, 1, 2, or 3, right? That right there. Now I could do this by doing a binomial PDF for 0 and 1 and 2 and 3 and then adding them, because it's 0 or 1 or 2 or 3 and we could add. But the calculator has a cumulative total function that does from 0 up to and including the 3 in a single step. That would be the binomial CDF, C for cumulative total, and that would be out of 6 trials, again, 0.5% chance of success having a tail, up to and including the 3, right? So that is located in the same place as the binomial, so second vars, but it's the next one down. After binomial PDF, there's a binomial CDF. Same entry, 6 trials, 0.4 chance of success, up to and including 3, and that would be 0.652, about 6563, 0.6563, something like that, okay? All right, and the last one says, what's the probability that at least 2 tails appear? So at least 2, right, would be from 2 on up, right, from 2 on up. All of these trials right here, these trials, right? But we know that those trials plus these trials add up to 1. So the way I'm going to solve that problem is I'm going to say the probability, the probability of having at least 2 tails is equal to 1 minus the probability of having up to 1 tail appear. So we're going to do 1 minus, and then we'll use the cumulative binomial statement to get 0 and 1 added together. 1 minus binomial CDF out of 6, 0.5 chance of a tail of having a tail, up to 1. That will include, since I used the C, the 0 and the 1 case. Right? So in a calculator, you could do it this way. You could say 1 minus, and then do the binomial CDF function out of 6 trials, up to and including 1. And that would give you 1 minus 0.1094, which is, let me just write this out. This is 1 minus 0.1094, and so that turns out to be 0.8906. So the nice thing about these problems is once you identify what a success is and you can use the model, it's actually less work than the previous lessons by hand calculations with the foundational problems. So we did 4 complicated problems there fairly quickly. Okay, let's move on to the next one. The next one says, a game of skill at a county fair consists of throwing ping pong balls into buckets. A game consists of throwing 4 balls at the buckets, and to win, the player must have all 4 balls land in a bucket. On an individual throw, the ball lands in the bucket 30% of the time. So the questions are, if a player plays this game 1 time, what's the probability they'll win that game? And then if the player plays the game 5 times, what's the probability they'll win at least one of the games? And then an older sister is determined to win the prize, which is a stuffed animal for her little brother. How many games on average should she expect to have to play in order to win the prize? Okay, so pause the video, give this a try. Okay, so as I look at this, right, the first case, right, we're talking about we're playing a game where we're just going to play a single game, right, which means we're going to throw the ball 4 times, right? So in this case, I'm going to ask myself, do I have one of these special models? Do I have a yes or no situation? Yes. And the yes is going to be that we have 1 ball go in to the bucket, okay? So we're talking about within a single game, right? Is the probability constant and independent, right? That's yes, because they said that the probability of success is 30% of the time. 30% of the time, a single ball lands in the bucket, and the presumption is that that's true every time you play, right? Do I have a fixed number of trials? Right? I think I do in this case, yes, because the number of trials is 4, right? We have 4 trials specifically. So that makes this a binomial situation, right? And that means that I could define my random variable to be the number of balls that go in, right? And then what is the possibilities? I could have none go in, 1, 2, 3, or all 4 of them go in, okay? Okay, so, and I could find various probabilities for that. So what we're asking is, what's the probability that we win the game, right? But winning the game requires that all 4 go in. So we have to have 4 go in for that to happen. And that's an exact case, the probability of exactly 4 going in. So that means I'm going to use binomial, actually let me write this below this, right? We're going to use binomial PDF because the P version, because it's a single case, right? So the number of tosses we have is 4 that could go in. The probability of it going in is 30%, so that's my probability, and we want the probability that exactly 4 go in, all 4. So we would go to the calculator and do binomial PDF. Out of the 4 tosses, if there's a 30% chance of a ball going in, have all 4 go in so you win the game. That's 0.0081. 0.0081. So there is a less than 1% chance that you're going to win a game. 0.8% chance, not a very likely thing. Okay, for the second part, it says now the player is going to play 5 games, right? What's the probability that they'll win at least one of the games? So the random variable here is not going to be the number of balls going in buckets. It's going to be the number of games that are played, right? So I could say, well, do I have a yes or no situation? Yes, right? What we're talking about is yes equals winning a game, not a ball going in. And is the probability constant and independent? That's yes. And the reason is because now I know that the probability of winning a game is what we found in the first part. The probability is 0.0081 of winning a game. We'll use the probability from the first part. Okay, and then do I have a fixed number of trials? Yes, because we're trying 5 games. And we want to know what's the probability we'll at least use one of the 5 games. And so again, this is a binomial situation. So now I'm going to define my variable, not to be my random variable, not to be the number of balls that go in, but the number of games that we win. This will be the number of games that we win. Right? And the possibilities are we could win none of the games, 1 of the games, 2 of the games, 3 of the games, or 4 or all 5 of the games. And we could find probabilities for that. Right? So we want, in this case, the probability of winning at least 1. So at least 1 is all of this over here. 1, 2, 3, 4, 5, or 4 or 5. All of those could be there. So we could do this with a binomial PDF for each one, for 1, and then a separate one for 2 and 3 and 4, but add them, right? But I'm just going to take advantage of the fact that that plus this adds up to 1. So I'm going to write it this way. The probability of winning at least 1 is equal to 1 minus the probability of the opposite, winning none, winning 0 games. Because now I can solve that. I could use 1 minus. I'll use binomial PDF. Now I'm going to use P for this 0, although you could also use C, because both of them are just going to go from 0 up to 0 and include that one case. I'll choose to use P because it really is just one case. Right? Out of 5 games, the probability of winning one of the games is the 0.0081 that we found in part A. And then we want the probability of winning 0, right? So if you plug that in your calculator, you end up getting that is 0.96015. In other words, your probability of winning none of the games is 96% of the time, right? So 1 minus that is 0.0398. So this is the probability that you would win at least 1 game if you played it 5 times. So you're up to 3%. Playing it 5 times, right, means you have about 4%, about a 4% chance. Okay. So the last question says, the older sister wants to win this stuffed animal prize for her younger brother. How many games should she expect to play in order to win? So for this one, we're going to say, I'm going to focus on the word expect. That should lead us to think we're finding the expected value, right? The expected value. So for part C, I'm really trying to find the expected value. And it's the expected value of a binomial distribution, right? Well, I don't know. Is it a binomial? All these other things have been binomial. But if you think about it, right, we wouldn't play a specific number of games, right? We're just going to keep playing games until we win. Now that's different, right? If we're playing until we win, until we have success, and we're wondering when is the first time that we have a success, right? Until we win, and then we'll stop, that is actually a geometric situation, right? The difference between binomial and geometric is binomial is out of a fixed number of trials. We want to know something about the number of trials that are successful, right? Geometric has to do with we keep playing until we get a success, and that's what we would do in this scenario. So what I really need is the formula for the expected value of a geometric probability distribution. And if you look it up in your notes, that turns out to be 1 over p. Okay, that's discussed in the geometric probability lesson. So all I really have to do is figure out what 1 over p is, right? The expected value would be 1 over the chance of success. Now, we're talking about how many games should she play. So I have to use the probability of success for winning a game, which would be the 0.0081. So it's going to be 1 over 0.0081, which turns out to be 123.4. And that means that she should expect to play 124 games before she will win that stuffed animal for her brother, okay? Now, this is how carnival games stay in business, right? Maybe it costs $1 to play each of these games, right? So you should expect to lay out $124 to win this probably $3 stuffed animal for your little brother. It would probably be cheaper for you to just go buy the stuffed animal, right? Unless you really have fun playing the games, of course. Okay, let's move on to the next one. The next one says we have a pair of fair six-sided dice are tossed 4 times. We want to find the probability that the sum of 9 or higher appears at least twice. So pause this and then give it a try. All right, so we'll check our yes-no situation, the conditions for the standardized models. Do we have a yes or no situation? Yes, and we're talking about the sum of 9 or higher appearing, 9 plus appearing. Okay, so you either have a sum of 9 or higher, that would be the yes case, and the no would be that we have a sum that's not 9 or higher, that's below 9. Okay, is the probability constant and independent? Is that true? Since dice are being tossed, I think that's always true, right? And the probability, what would it actually be? Well, let's stop for a second and think about that. What would the probability be if we toss a die and we're talking about a sum? So if I toss 2 pairs, so 2 six-sided dice, a great way to represent that is with a grid, right? I could have a 1, 2, 3, 4, 5, or 6 on the first die, 1, 2, 3, 4, 5, or 6 on the second die, and then I can figure out what the possible sums are. Well, if I had a 1 and a 1, that would be 2. A 1 and a 2 would be 3. And so I can quickly fill in all these sums by adding things up. Let me just do that really quickly. This is a great way to picture what happens when you toss 2 dice. 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 12. Okay, so how many of those are sum of 9 or higher? So that would include the 9s and everything above the 9s, right? So there's 6 by 6, right? There's 36 different possible sums, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So 10 out of 36. That's the probability that we would have a sum of 9 or higher. And let me just quickly convert that to decimals. 10 out of 36 would be 0.2777. So I could say the probability of success is constant, and it's 2778 approximately. Okay? And then the last one is, do I have a fixed number of times? Well, we're tossing specifically 4 times. So we do have a fixed number of trials, right? And that means that we're talking about a binomial situation. Binomial situation. Okay, so that gives us a strategy. That means the random variable is going to represent the number of tosses which have a sum of 9 or higher. 9 or higher. Okay, and so the possible values of that would be we could have none of the tosses, 1 of the tosses, 2, 3, or all 4 of the tosses, right? And so find probabilities. We want now the probability that this appears at least twice. So at least twice is 2 or higher. We're trying to find this probability over here. I could do that by doing binomial PDFs for 3 things and adding them, or I can take advantage of the fact that these things add up to 1. So the probability of having some 9 plus at least twice, that's equal to 1 minus the probability of having the sum 9 plus 0 or 1 times, right? Which could be done with binomial CDF to get the cumulative total of 0 and 1 together. So out of the 4 tosses here, the probability of that happening is this 0.222777 repeating. And then we want the probability up to and including the 1. All right, so that turns out to be, when you put it in a calculator, 0.3094. That's how we would do that problem. Okay, let's move on. So the fourth problem says, in a survey of U.S. households about cell phone ownership, the following data was obtained. There's different number of cell phones, 0, 1, 2, 3, 4, or 4 or more, and then the probabilities that we found. Find the probability of a household having 1 or 2 cell phones, 2 or more cell phones, fewer than 2 cell phones. So pause and then unpause. Okay, so it's really tempting when I have something that looks like a random variable and then a probability to assume that this is one of those distributions where we can actually use all of the different numbers, as if they were binomial. Like seeing a table like this, it makes us think, oh, this is definitely a binomial problem because I have a fixed number out here, right? But this is actually not a binomial problem. I put this one in specifically just so that you can see that just because I have something that looks like I've got a random variable and a probability, it is not always a binomial, right? Why is it not binomial? Well, let's see. First of all, we don't have a fixed number of trials here, or if we don't have a fixed variable value because it's 4 or higher, although we did group that into one case, right? We don't have probabilities being constant here. Yeah, this doesn't follow the model. If you were to look at a particular binomial model, there's no binomial model that matches those probability numbers. So the good news is they did give us the probabilities. So this is just drop back to OR cases, right? For part A, if I want the probability of having 1 or 2 cell phones, then I can just remember that the OR rules are probability of 1 plus probability of 2 minus the probability of 1 and 2 at the same time, right? But since we're talking about a family, right, we can't have 1 and 2 cell phones. They either have 1 or they have 2, so that's nothing. And all I really have to do is just add up the probabilities of 1, which they told me is 0.23, and 2, which they told me is 0.35, and so that turns out to be 0.58. So this is just simply adding up the probabilities they gave us. We don't have to use any standardized model at all because they gave me the standardized model, or they gave me the model, not the standardized model. Probability of 2 or more cell phones, 2 or more, just means we're going to add, let's see, the 2 case, which is 0.35, to the 3 case, which is 0.28, which with the 4 or more case. You just add those numbers together, and you get 0.71. And then for C, it says the probability, oh, sorry, I keep saying equals there, the probability of having fewer than 2 cell phones. Well, that's just 0 and 1, so I'm just going to add those 2 probabilities up, 0.06 plus 0.23, 0.29. All right, so I threw this in just so that you don't automatically think that something in that form has to be binomial or geometric or Poisson. It's not. Okay, let's look at another problem. This one says a produce vendor receives a crate containing 40 apples. If 8 of the apples contain worms, although it is not possible to see which ones contain the worms visually. If a vendor randomly selects 12 apples to fulfill an order, what's the probability that exactly 3 of the apples in the order will contain a worm? So pause this and then go ahead and try this problem. Okay. So this is also kind of a trick question. You would think that because of wording like exactly 2, that this one is also going to end up being a binomial or a geometric, but actually this is another case where none of the standard models work. And we can kind of see why that's true. If I go through the kind of table of things, right, do I have a yes or no situation? Yes. We want to find, yes would be that a certain number contains apples, right? Would be that we have, well, let's see, that exactly 3. Well, no, it would be that the probability of an apple containing a worm. So an apple containing a worm, right? So we have that, right? We can figure out that probability, right? But because we have a small sample size, right? Once I select one apple, then that means the probability of the next apple containing a worm is not the same, right? Here's the situation. We have 40 apples. In other words, if I'm asking is the probability constant, I'm going to say no, and therefore I can't use a standardized model. To show why that's true, right, let's say we have 40 apples, and 8 of the apples have a worm, and therefore 32 of them have no worm, okay? And then in my sample, I have to select 12. I have to select 12 apples, right? So if I select an apple, right, the first one, what would the probability be of the first one containing a worm? Well, that would be 8 out of the 40 apples. That's the probability of the first one containing a worm. But once I've selected that apple, if I selected a worm, then the second time the probability would be now 7 wormy apples out of 39, right? But if I didn't get a worm the second time or the first time, then the probability would be 8 out of 39, right? This probability depends on whether we got a worm or no worm back here, right? And that means that the probability of being constant is not fulfilled. This is not like a coin that has no memory. Here, we're talking about apples, and and it's a fairly small group of apples, 40. So once I select one, the probability of the second one having a worm is different. Okay. So we're going to have to use a different technique here. We're going to have to say, all right, if I want to have exactly 3 of the apples in the selection having a worm, then that means the other 9 will have no worms, right? And so we're going to talk about the idea of like the event being the selection of the entire 12 at once. And all groups of 12 apples are equally likely to be selected. So this is an equally likely case, really. If you approach it this way, it's equally likely to select any 12, right? So the sample space would be all the number of ways to select 12 apples. Okay, so how many ways would that be? Well, we're going to select 12. Let me change colors here. We're going to select 12 out of the entire 40, right? And they can be, it doesn't matter what order I select them in, they just end up in my basket. So we could use a combination, right? If you're selecting something and when you select it, it gets used up, that means that out of the 40 apples, I could use a combination. 40 combination 12. That turns out to be the number of ways to select 12 apples out of the 40. Now, for the sample space, or that was for the sample space. For the event space, where I specifically have to have 3 worms, that means I have to have some that have worms, and I have to have some that have no worms, right? And the ones that are worms have to be selected out of the wormed apples, and the ones that have no worms have to be selected out of the ones that don't have apples, don't have worms. So that would mean out of the 8 wormy apples, I would have to select 3 of those, and order doesn't matter, so that's a combination. And out of the 32 non-worm apples, I would have to select 9 of those. And then we'd have to combine these choices with these choices, so the multiplication principle says I multiply those. And that means the probability of getting exactly 3 that are wormy, right, is going to be 8 combination 3 times 32 combination 9 over 40 combination 12. That turns out to be, if you plug it in your calculator carefully, 2811. And again, I wanted to throw a problem in here just to show that just because you see wording like exactly 3, that doesn't mean that it's definitely going to be a binomial or a Poisson or a geometric problem, right? If the probability is not constant, once you get away from things like dice rolls and coin flips and things that are constant probabilities, then we have to use other techniques. Okay, let's go back. Now this one, I will tell you, is solved with one of those standard models. Okay, so it says a person gives a friend their key ring and tells them to go on ahead and open the front door. So there are 8 keys on the key ring, and the person does not tell their friend which key opens the door, so the friend has to try keys at random till they find one that works. What's the probability that the friend must try more than 4 keys before the door opens? So pause and then try this problem. Okay, so let's do our little test again. Is there a yes or no situation here? Y means that we find the key that opens the door. So the key either opens the door, an individual key, or it doesn't open the door. Okay, is the probability of that constant and independent? Well, I think so, because if there is, if we have no idea which of the 8 keys opens it, then any one key has a 1 out of 8 chance of opening the door. And it would presumably be the same. So I'm presuming that the keys are not visually so different that you would be able to tell, okay, this one's definitely not a house key. Assume that they're all the same kind of a key, so you can't discern between them. Then each one has the same 1/8 chance. Do we have a fixed number of trials here? The answer to that is no. We're not going to try all 8 keys. We're going to keep trying keys until we find the one that opens the door, and then we'll stop, right? We will stop when we have success. Well, when we're trying to figure out how many things we have to try in order to get success, that means that's the geometric case. This is the case where we get to use the geometric model instead of the binomial model. Okay, so the random variable is going to be the which key opens the door. The door. Okay, is it going to be the first key? Or is it going to be the second key, or the third key, the fourth key, the fifth, sixth, seventh, or is the last key the 8th key? And there's no 0 here because you have to try one of the keys, right? So geometric starts with 1. and then we have probabilities for that. So we're trying to find the probability that the friend must try more than 4 keys. So more than 4 keys would be this part of the distribution from 5 on up to 8. So I'm going to use the fact that they add up to 1 and say the probability that we have to try more than 4 is going to be 1 minus the probability that we try 0 to 4, up to 4. Okay? So 1 minus, this time we're going to use the geometric, geomet, and since I'm going to combine a number of trials here, I'll use the C version, CDF, right? Now, the geometric one, we don't have a total, so we just give it the probability of success, which is 1 out of 8 chance of any key working, and then we have to give it the number of trials we're going to go up to. So this would be up to and including the 4th key, so 4. Now, where is that in the calculator? Geometric CDF is in the same spot as binomial, second variables. I'm going to scroll from the bottom. It's actually at the bottom of the list here, Geomet CDF. And you would enter the probability 1 out of 8, and then this would be 4. So the probability there is 0.4138. So this is 1 minus 0.4138, which turns out to be 0.5862. So there's about a 59% chance that the person is going to have to try more than 4 keys before they find the one that opens your door. Okay, just a few more problems here to go. Let's try another one. It says, if the odds for winning a horse race are 7 to 3, and a person betting will win $10 if their horse wins, then how much should the person have to bet in order for the game to be fair? Fair means that if they bet on this race many times, they would break even in the long run. Okay, so pause this, give it a try. Okay, so this, it says for fair, we want to have a fair game. Whenever we talk about that, I'm hoping that you think fair relates to the idea of expected value. If we can find the expected value for winning, then what we should bet should be exactly equal to what we'd expect to win on average. And if that's true, the game is considered to be fair. So, so what do we have here? We don't really have a standardized distribution, right? This is not the same probability every time and things like that. It's just that we're told that the odds to win are 7 to 3. So if I wanted to convert that to the probability of winning, that means we'll win 7 times out of a total of 10 times, because this is wins and the 3 is losses. So 7 out of 10. So there's a 70% chance of winning. And if I were to make a random variable that represents the dollars that we win, right, the possible values of this variable would be we could win $10, right, or we could win nothing. We either win or we lose. If we win $10. So what's the probability of winning? Well, we just said that that's 70%. And the probability of losing would be the other 30%, because you either win or lose here, right? So then I need to find the expected value. So the expected value, there's a couple ways you could do it. I would do this by hand. The formula for discrete expected value is the sum of each of the data values times the probability, like that. So if I took the data value $10, that happens with a probability of 70%. And then I took the data value $0, and that happens with a probability of 30%. Then that turns out to be, let's see, $7. And so we should have to bet $7 to play, because on average we're going to win $7. We won't actually ever win $7. We'll win 10 or 0, but in the long run it'll average out to $7 a play. So if we're spending more or betting more than $7 per play, we're going to lose money in the long run. So this is kind of one way to find the expected value of a discrete distribution like this. The other way is to consider this to be a data set and to use the calculator statistics functions for doing this. So there's another way to find the expected value. It's really the mean of this distribution. Expected value, typical value is the mean. So you could use list. You can go stat edit in a calculator and put the possible data values here, which are 10 and 0, right? 10 and 0. So in list 1, I put you could win $10 or you can win $0. And if I scroll over here to list 2, I could say the probability of winning 10 is 70%. And the probability of winning 0 is 30%. And then I could go to stat, over to calculations, one variable statistics, and then run that where list 1 contains the data, and the frequencies or probabilities are contained in list 2. And if I hit enter, it tells me the average of this distribution here is 7, right? This is telling me that the average is 7. And that's another way to get that 7 is the typical value or the average value. Okay? Okay, let's keep going here. Let's see, I should probably get rid of that. Okay, another problem. It says a toy store has found that about 3% of the toys it receives from a certain toy factory are defective. If they receive a shipment of 800 toys, how many of these toys should they expect to be defective? Okay, go ahead and pause and give that one a try. Okay, so again, there's that word expect. That how many should we expect to be defective? So I believe that means we're talking about an expected value, just like we were in the last problem. But in this case, we might be able to get by with one of our standard models because it didn't really give me, it gave me a 3%, but that's an overall percentage, right? Okay, so let's see whether or not this fits the criteria for binomial or geometric. Is it a yes or no situation? Yes. Yes equals that a toy is defective. Toy is defective. Okay, what's the probability? Is it constant and independent? Well, they said the probability of any individual toy being defective is 3%. So presumably this is a large sample, and if I pull a single toy out, it doesn't change the probability that the next one is going to be defective, right? We have 800 toys, so removing one doesn't really dramatically affect or significantly affect the probability of the next one being. So you can assume this 3% is the probability of all the toys being any individual toy being that. So that's true. And then do we have a number of trials, right? The number of trials here, right, it is fixed because we're talking about specifically 800 trials. Okay, so that makes this a binomial situation, right? But we're still talking about needing to find the expected value. So I really just need the expected value of a binomial distribution, right? Well, I mean, you could think of it this way. You could say I could say that I have X is the number of toys that are defective, right? And say I could have 0 toys defective, 1, 2, all the way up to 800 toys defective, right? But what I'm really trying to do is saying, what's the most typical or expected value here? Which of these values in here is the most typical value I should have? What's the expected value? Okay, so you go look up the expected value formula or the formula for the mean of a binomial distribution, and that turns out to be n times p. And it's kind of intuitive why that's true, because if I have 800 toys, that's the n, and there's a 3% chance that any of them are defective, then I should expect about 3% of the 800 toys to be defective. So I just multiply 3% times 800, all right, I end up getting 24, right? So that means we should expect 24 toys to be defective in this group. It's just the mean of a binomial distribution. Okay, I think we have 3 more problems here. Let's keep going. If the average hurricane frequency is 8 hurricanes per year, what's the probability the randomly chosen year would have at least 2 hurricanes, or have more than 10 hurricanes, or exactly 8 hurricanes, exactly the average number? So pause and try this problem. Okay. Again, since this is about a binomial and geometric, we should see whether or not we can apply those. And we also have Poisson. So let's see. We have, is this a yes or no situation? Yes. A yes would be that we have a hurricane in the season, right? What about the probability? Is it constant and independent? Okay. Well, actually, I don't see any probabilities in here. It says the average hurricane frequency is 8 per year. It doesn't say 8 out of a number. It's not like there's a maximum possible number of hurricanes you could have, right? So we have the number 8, right? What does that really represent? That 8 represents the typical number, right? We could say the typical number of hurricanes equals 8, but we don't have that as a probability. So I really have no probability here. There's no p. And that means that I can't use geometric and I can't use binomial, because both of those require that I have a fixed probability, right? That's independent and constant. So that means I'm going to have to use the Poisson model. The Poisson model is useful in this case because if I have information about the typical value, that typical value is called lambda, right? Lambda is the typical number of hurricanes, the typical value of the successes, number of successes. So that would be 8. So we do know that the typical value is 8. We can use binomial. Okay, so that means for part A, right? Actually, for all of them, I could do this. I can say, let's have a random variable be defined that represents the number of hurricanes, right? And we could have no hurricanes, or one, or two, or three, or four. Actually, let me write this over again so I can spread this out a little bit. X is the number of hurricanes, right? And so it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or more, right? There's really no limit to how many hurricanes you could have, right? And then we'll talk about probabilities for those things, right? So the first question's asking, it's asking, let me use this color. It's asking, what's the probability that we have less than 2 hurricanes, less than 2. So less than 2 is just 0 and 1. I could do that by using a Poisson PDF function for 0 and 1 and adding them up, right? Or I could use the fact that I could take the cumulative total up to 1 and just go straight to the Poisson CDF model. So the CDF and PDF, all that stuff works the same way as binomial and geometric. Poisson CDF, right? But in the Poisson model, you have to specify the lambda value, right? Which in this case is typical number is 8, and we want the probability that up to and including 1. So 0 and 1, right? Is that right? So probability of 0 and 1. Yeah, was it less than 2? Less than 2. Okay, so let me show you where that is on the calculator, right? Also in the distributions menu, if I scroll up from the bottom, there's a Poisson PDF and a Poisson CDF. So I'm going to use the Poisson CDF, right? The lambda value, the typical number of hurricanes, is 8, and we want to go up to and including 1. So that would be 0.0030. 0030. 0.0030. So less than, there's only about a 0.3% chance that we'll have less than 2 hurricanes in a season if 8 is typical. Okay, the second part says find the probability that we have more than 10, greater than 10, right? So greater than 10 would be way out here, and I'm going to use the fact that that plus this would add up to 100%. So that's going to be 1 minus the left-hand side, which we could use Poisson CDF again. This time, again, 8 is the typical number that we go up to and including 9, right? So 1 minus Poisson CDF there. And if you, let's do that in the calculator. So the Poisson CDF number is, let's go Poisson CDF, right? 8 is typical. We want to go up to and including 9 because it said more than 10. Okay. So that would be 0.7166. So it's 1 minus 0.7166, which turns out to be 1 minus that previous answer is about 0.2834. 2834. So there's about a 28% chance of having more than 10 hurricanes. And then the last probability, we're asking what's the probability that we have exactly the typical value of 8. So this is an exact case. So for the probability of having exactly 8, we're going to use the Poisson PDF version. The P versions of these formulas give a particular single value, right? So if 8 is typical, the probability of having exactly 8 would be that. And so that's also in that same spot, except we choose the P version this time. Out of 8, typically, to have exactly 8, turns out to be the probability is 0.1396. So that's kind of funny, really, if you think about it, right? There's typically 8 hurricanes in a season, but that only happens in 14% of the years, right? Typical doesn't mean that it happens more than 50% of the time. It just means it's the highest individual percentage, right? Okay, let's keep moving then. So the next one would be a complaint call center usually receives around 100 calls per hour. Incoming calls are routed to one of 10 operators for servicing. What's the probability that one of these operators will have to process more than 100 calls in an 8-hour shift? So pause and give this a try. Okay, so again, we'll test to see whether it's applicable to use our models. Is this a yes or no situation? Yes, a receiver receives a call or processes a call, right? Is the probability constant, and is it independent? Can we associate something with that? It says a call center usually receives around 100 calls per hour. that's serviced by 10 operators. I don't have anything that's directly a probability in here. So I think I'm not going to be able to assess that directly. I'm going to say no, because I don't really have a probability. I might be able to figure out a typical amount, though. The question's asking us whether one operator has to process more than the number of calls. So this yes really is a call for one operator, right, specifically. So what I could do is say, let's figure out the typical value for one operator, right? So if we have 100 calls per hour in the center, right? And then, let's see, that's per hour. And then a shift consists of an 8-hour shift. Okay, so if I multiplied by 8 hours, that would give me the number of calls, period, for the whole center. But then it says that there are 10 operators, right? So if I divide that by the 10 operators, if I took 100 times 8 divided by 10, that turns out to be 80 calls per operator in a single shift. Not 80, not 8, 80 calls, right? So that's our lambda number. Lambda is for one operator to receive 80 calls typically. Okay, that means we can use Poisson. We are able to come up with a typical value that relates to the quantity we're finding. It would be 80 in this case. Okay, so what have we got? We've got a random variable that represents the number of calls for one operator, and they could receive no calls all the way up to any number of calls. The typical number, lambda here, is 80. Presumably it could go well above that, 100, 200, something like that, and then these are probabilities associated with that. So we want the probability that we have to process more than 100 calls. So more than 100 means from 101 on, this part up here, let me change colors, right? This part up here from 101 on. And so that plus the left side adds up to 100%. So the probability of one operator having greater than 100 calls is going to be 1 minus the left probability of the operator having less than or equal to 100 calls. Less than or equal to 100 calls. Okay, so that would be 1 minus, and then we'll use Poisson CDF to get all of these. And the lambda value we said was 80, and we want to go up to and including 100. Okay, so if you plug that in your calculator, it turns out to be 1 minus 0.9868, and that turns out to be 0.0132. So if the typical number of calls that one operator receives is 80, then the probability that an operator has to receive more than 100 would be only 1.3% chance. Okay, just one more problem in this video. Trying to give a variety of different kinds of problems. These models are so flexible, you can use them in a lot of different ways. It says, Jesus and Olivia are taking a 20-question multiple choice test. Each test question has 4 answer choices, A, B, C, and D. Jesus studies diligently and estimates that he has an 80% chance of getting any of the questions correct on the test correctly. Olivia didn't study at all and will therefore be guessing on all the questions. So students must score at least 60% on the test in order to pass. What's the probability Jesus will pass, and what's the probability that Olivia will pass? Okay, so go ahead and pause and try this problem. Okay, so does this fit our standardized models? Well, yes or no. Yes, this is a yes or no situation. Yes would be that we get one question correct. One question correct, right? Because this has to do with passing, and we'll have to know something about the number of questions that would have to be correct for us to get this to pass the test. So if we define one question being correct as getting yes, then the opposite is no, so it's a yes or no situation. Is the probability constant? And is it independent? Well, they only give a single percentage chance, so presumably that's the same independently for every question. And the probability of success will be different depending on who we're talking about. So for Jesus studied, and so his probability of success, his p-value will be 80%, right? But for Olivia, she didn't study, So if she didn't study, that means she'd be completely guessing. Since there are 4 answers, she has a 1 in 4 chance or a 25% chance of getting a question correct. So that would be her probability of success. But presumably, when we do each person's probability calculation, that probability is constant and independent from question to question. So what about the number of trials? The number of trials, that's fixed because we're talking specifically about 20 questions, so n would be 20. And that means since we have a fixed number of trials and the other things are true, this is a binomial setting, so we can use binomial model for this. Okay, so we're just going to do each person individually, right? The random variable for here will be that Jesus gets a question correct, or the number of questions that he gets correct, right? He could get none of the questions, 1, 2, 3, all the way up to all 20 correct. Random variable is the number he gets correct. And so the probability, we want the probability that we'll pass the test. So we have to have a 60% on the test. If it's a 20-question test and we have to get 60% correct to pass, then the 60% turns out to be 12. We have to get 12 or higher, right? 12 or higher in order to pass. So in this, if I put a line here at 12, right? 12 or higher would mean passing, right? And up to and including 11 would be failing. Okay, so for finding the probability that Jesus passes, it's going to be the probability of getting 12 or more correct, right? Which is a right-hand probability, so that's going to be 1 minus the left-hand probability of getting 0 to 11 correct. And for Jesus, so we'll use binomial CDF again. Out of 20 trials, 20 questions, Jesus' probability of getting correct is 0.80. And we're going to go up to including 11, so we get everything except the 12 and on. And so if you plug that in a calculator, that turns out to be 1 minus 0.0998, which means Jesus' probability of passing the test is 99%. Okay? If we do the same thing for Olivia, it's the exact same diagram. We want the probability of 12 plus, but this time for Olivia. The only thing that changes is the probability of a question being correct is not 80%, now it's only 25%. So we have to change her probability of success. That becomes 1 minus 0.999, let's see, 1 minus 99906. So her probability turns out in the calculator 9.3539 times 10 to the negative 4th, which is 0.000935. So by randomly guessing, she has far less than a 1% chance of passing this test. Okay, so a lot of different problems related to the binomial, geometric, and Poisson, and kind of distributed typically. The binomial model is used far more often than the other two.